Good evening everyone. So welcome to my YouTube channel Mathshastram. So today we are going to start a new topic that is called infinite series. So this is the first lecture on this. So let's see what is infinite series. Infinite series, you can say series also. Both are same. Infinite series. An infinite series series is a sum of sequence an given by a1 plus a2 a3 plus an. Okay. So an infinite series is a sum of sequence is a sum of the sum of terms of a sequence an given by this. Okay. Note that a series is a series summation n goes to 1 to infinity is identified by the sequence an. It means a series is identify a sequence. So therefore, given a sequence an, the corresponding series is given by summation n goes to 1 to infinity an. The series summation n goes to 1 to infinity an is called a series, or you can say infinite series corresponding to the sequence is an. What is partial sum? Partial sum. Given a series, or you can say infinite series, because series means infinite series. Summation n goes to 1 to infinity an. We write Sn is equal to m goes to 1 to n am. It means the sum of first n terms of the sequence an. Okay. Then Sn is is also a sequence, and Sn is called nth partial sum of the series n goes to 1 to infinity an. Okay. Nth partials of the series. Note convergence of a series. A series summation n goes to 1 to infinity an is said to be convergent if the sequence of partial sums Sn converges to is convergent. Is convergent. Okay. In other words, if Sn converges to L, we say that this series converges, and we call L the sum of this series, and write sum n goes to 1 to infinity an is equal to L. Okay. Example, you take this series n goes to 1 to infinity 1 upon n into n plus 1. Okay. Then what is an term? An is 1 upon n plus 1. Okay. For all n belongs to n. Now this a1 is 1 into 2. I can write it 1 minus 1 upon 2. Okay. And what is a2? A2 is 1 upon 2 into 3. 1 upon 2 into 3, that is 1 by 2. 1 by. What is a3? 1 upon 3 into 4. 1 upon 3 and minus 1 upon 4. And so on. am minus 1 is m minus 1 is 1 upon m minus 1 m. How I can write this m minus 1 upon m. What is am? This is 1 upon m plus 1. What is this? 1 upon m minus 1 upon m plus 1. So if I add all these terms, a1 goes to am, then what will be happen? You see that 1 by 2 is cancelled out, 1 by 3 is cancelled out. Okay, so 1 by 4 will also be cancelled out by next. Okay, so this way these are cancelled out and this will be also cancelled out. So what is so this implies a1 plus a2 plus a3 up to am minus 1 plus am is equal to 1 minus 1 upon m plus 1. Okay, so what is this sum? This sum is Sm and this is 1 minus 1 upon m plus 1. Okay, now see that Sm tending to 1 as m tending to infinity. So this implies Sm converges to 1. Okay, hence the series hence the series summation n goes to 1 to infinity 1 upon n plus 1 is convergent and its sum is n goes to 1 to infinity n plus 1 is what is this? This is 1. So this is the answer. Okay. So example 2. Summation n goes to 1 to infinity 1 upon 2 to the power n. Okay. So what is an? It is 1 upon 2 to the power n for all n belongs to n. So what is Sm? What is Sm? Sm is equal to summation n goes to 1 to 1 upon 2 to the power m. So what will be this? So this is 1 by 2. First term is 1 by 2. Then 1 minus 1 2 to the power m upon 1 minus 1 upon 2. Because this is a geometric series. The sum is this. So after solving it, you will get. Okay. So this is 1 by 2. So 1 by 2 is 1 by 2 cancel out. So Sm is equal to 1 minus 2 to the power m. So this stands to 1 as m tending to infinity. Okay. So this implies the series n goes to 1 to infinity 1 upon 2 to the power n is convergent and limit of and sum is 1. Summation n goes to 1 to infinity 1 upon 2 to the power n is 1. So this is the answer. Okay. So necessary condition for convergence. Okay. Let summation n goes to 1 to infinity a n is b a convergent series. Okay. Then a n tends to 0 as n tending to infinity. It means nth term of a convergent series tends to 0 as n tending to infinity. Okay. Let's see. So I'm writing is if this series is a convergent series, then nth term tends to 0 as n tending to infinity. Okay. Okay. So one thing you note that here, this is not actually what was SM. So SM was so this is this example of n goes to okay. So necessary condition for convergence. If series is convergent, then nth term tends to 0 as n tending to infinity. It means nth term of a convergence series tends to 0 as n tending to infinity. So let's see its proof. Put so what is Sn plus Sn? What is Sn? Sn is summation m goes to 1 to m am. And what is Sn plus 1? Am. Then now given that the series summation n goes to 1 to infinity, an is convergent. Therefore, Sn tends to L, and consequently, so if Sn tends to, therefore Sn tends to L, so if Sn tends to L, then Sn plus 1 also tends to L, because there is no distinction adding a 1 in infinity. We also have Sn plus 1 tending to L. Okay. Now An is nothing but S. So one thing. So what is this actually? Sn minus 1. I should write Sn minus 1 here. So this is Sn minus 1. So if Sn tending to L, Sn minus 1 it also tends to L. Now Sn, this is nothing but Sn minus 1. So this implies limit n tending to infinity An is equal to limit n tending to infinity Sn minus 1. So what is this? This is equal to limit n tending to infinity Sn minus limit n tending to infinity Sn minus 1. This is L. This is also L. So this is 0. So this implies limit n tending to infinity An is equal to 0. This implies An tends to 0 as n tending to infinity. That means An tending to 0. Okay. So now what is the meaning of this result? So remark, if this series given, if is given series and let be a series, if An does not tend to 0, then this series is not convergent. Because if a series is convergent, then nth term always tends to 0. If nth term, if you know that for a series, nth term is not tending to 0, that series cannot be convergent. Okay. For example 3, this series, summation n goes to 1 to infinity, n plus 1 upon n. So An is equal to n plus 1 is there. That is, what is limit n tending to infinity? An is equal to limit n tending to infinity, n plus 1 upon the limit . So limit n tending to infinity 1 plus 1 upon n, that is 1 plus 0, 0, sorry 1. So this implies an tending to 1. If an tending to 1, it is not tending to 0. It means an not tending to 0. So this implies this series n plus 1 upon n is not convergent. Okay. Example 4. Example 4. This series summation n goes to 1 to infinity cos 1 upon n. Now an is equal to cos 1 upon n. So what is the limit of n tending to infinity? An is equal to limit of cos 1 upon n, that is cos 0, that is 1. Cos 0 value is 1. So this implies an tending to 1. This implies an does not tends to 0. So this implies this series n goes to 1 to infinity n cos 1 upon n is not convergent. Okay. Now another thing, example 5. This series summation n goes to 1 to infinity n. Now see that what is an? An is equal to n. So this implies an tending to infinity. It means an does not tends to 0. Okay, an does not tends to 0. So this implies this series n is not convergent. Okay. So example 6, you see this series n goes to 1 to infinity minus 1 to the power n. So what is an? This is minus 1 to the power. So what is this an? So this is minus 1 if if n is odd natural number. Okay, and 1 plus 1 if n is even natural number. Okay, so limit n tending to infinity an is equal to minus 1, okay, and plus 1 if n is odd. So it gives two values. If n is odd natural number, and limit is always unique. Whenever limit exists, it is always unique. So this implies limit of an does not exist. Okay, so this implies, because this is oscillatory, this implies an does not tends to 0. So this implies is not convergent. So now we are going to prove a result. You can check theorem. Let summation n goes to 1 to n be a series with non-negative terms. It means an is greater than equal to 0 for all n belongs to n. Then either this series converges or either this series converges or diverges to plus infinity. Okay, let's see its proof. So there either this series is bounded above or unbounded above. Okay. Now first case, now this is either unbounded above or bounded above. Now first you observe that so one thing, sorry, I should write it again. So Sn is nothing but m goes to 1 to m am. Okay. So Sm is equal to n goes to 1 to m am. Okay. So either now you observe that Sm plus 1 minus Sm. What is this? This is Am plus 1. That is greater than equal to 0 for all m belongs to n. So this implies this sequence Sm plus 1 is greater than Sm for all m belongs to n. So what is the meaning of this? This implies this sequence Sm is monotonically increasing. Okay. This monotonically increasing sequence. Okay. So either Sm is bounded above is bounded or Sm unbounded. Now, case first, Sm is bounded. Now, in this case, Sm is monotonically monotone bounded sequence. Therefore, Y monotone therefore Y monotone convergence theorem Sm is convergent. If Sm is convergent, this implies this series An is convergent. Case 2, Sm is unbounded. Okay. Since Sm is monotonically increasing and unbounded. A monotonically increasing and unbounded sequence implies Sm diverges to plus infinity. It means diverges to plus infinity. Okay. So hence this series converges or diverges as either this series converges or this series diverges to plus infinity, provided An get non-negative for all and belongs to N. So this is proof. Okay. 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 So now this series, you see that example 7, this series cos 1 by n. So An is equal to cos 1 upon n, that is non-negative for all n belongs to n. And we already know that this series is not convergent. convergent. That means this series diverges to plus infinity. Okay, diverges to plus infinity. Okay, now example 8, you see this summation n goes to 1 to infinity, n plus 1 upon n. Okay, now an is 1 plus n upon n, that is non-negative for all n belongs to n. Now we have already checked that this series n goes to 1 to infinity, n plus 1 upon n is not convergent. Therefore, by theorem, the series summation n goes to 1 to infinity, n plus 1 upon n diverges to plus infinity. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next lecture.